Thank you for the introduction, and thanks for organizing this session, and also for very grateful for the NIH-NSF for have reviewed and funded this project. Everybody can see, and then I advance on this one. And so this is really a 10-minute overview of this project. And it's a great context to introduce this exciting project because of the context the previous overview provided. And just very quickly, the UT Health, University of Texas Health Science Center, is located in the Texas Medical Center, which is the largest medical concentration in the world. Here are by the number of different metrics. Here is what it shows. And the next several brief sections are really what we're instructed to do as a structure for the content. What is the problem that we're trying to address? And over the years, the NIH and other federal government has invested a lot of resources on developing health-related human data for advancing research. And everybody is familiar with image-based data. In this conference, probably everybody knows ImageNet. That's actually a key driver for deep learning. Here are two of the disease-specific data resources that I was fortunate to be part of and leading the informatics and data component. One is the Center for Sudden Death in Epilepsy, which is actually a 14-institution collaboration. The other is the National Sleep Research Resource that is funded by NHLBI as an R24 project. Unique to this data type is that it's actually physiological time series data. Both of the data set actually shares what's called a European data format, which is high resolution concurrent recordings of human physiological activity. You can have 10 to hundreds of high resolution channels recording those. As you can imagine, this is a very rich data set. It's a large, complex data set. And we've already made progress in annotating and collecting those data sets in a way that's usable, but it actually still presents fundamental challenges that's related to fairness and computation. On the left-hand side is actually the current way. It's still accessed this way. You make a request by searching metadata about which kind of the patient demographics and things like that. And then you identify that particular cohort and download the entire data file, waveform data file to your local storage. And then you parse them and chop them into minimum 4 pieces, label them, partition training set, testing set, and things like that. And then you get results. So data fragments, meaningful data fragments, happens in the local computer, local storage, using local computational resources, human resources. And then on the right-hand side, just as a brief example of, even to your end interest is in a very small, tiny piece of those waveform data, you still have to download the entire data file from the beginning and process everything at your own local place. And so if we have tens, hundreds of people doing the same, you can imagine lots of people doing exactly the same thing without realizing they're doing it. And the files gets downloaded, probably we're parking their local computer for forever, right? Wasting storage. So it's really applying strategically computer science kind of principle is refactorization. So extract the common needs and do that in one place, and then use that resource again and again, so that we have shared it, much like a cloud, in other systems. So with that kind of understanding, it's actually very simple to have a grasp of what should we do to make progress in this domain. Basically, we want to partition those signals into the proposed U2S self-descriptive format, what means that each smaller fragment comes with localized metadata. What time, what's the age of the patient, all of those, there's slight kind of redundancy in metadata, but metadata has a smaller footprint. So you localize the metadata with each of the fragment. And this, then you can store and process that. And the metadata or ontology associated with those fragments then can serve as inverted index, the key for the inverted index, not just forward index, but inverted index to facilitate rapid search and query visualization for that matter, because that's exactly the segment of interest now. With rich metadata, you can do that. And so that's transforming the existing paradigm to the one in this kind of narrowed proposed data format and database model. And so that's one major kind of platform development effort using a new kind of idea, new strategy. With that, we hope to be able to facilitate AI research, but then, as I mentioned, image-based machine learning and time series-based machine learning are very different things. So here you can imagine an example. We want to have a smartwatch for seizure detection, and you have many channels. One of the common approaches is actually to partition the time series into 30 seconds and convert each of the 30 seconds into an image. Spectral power and all that different signal analysis algorithms you can just apply here. You can have a quite rich image actually. And then what you end up is you have a lot of images, right? But then you use deep learning network to do your training, seizure, non-seizure, seizure, non-seizure, and you can get actually approaching precision recall of 99%. And based on publication, there are many publications on seizure detection, for example. But is that good enough for us? So we want to actually evaluate the science of the evaluation itself. What is the method that you use for evaluation? Well, now imagine you want to wear this watch and tell you seizure, non-seizure for the patient. And for 24 hours, you have how many 30 seconds? You have that many 30 seconds, right? Almost 3,000 frames of image for 24 hours. And then you apply the false alarm rate, you have the precision of 99%, you have 1% chance of getting it wrong. And then you have false alarm rate of almost 30 per day. That's annoying, that's unacceptable. To be just a rough reference, FDA approved class 1 and 2 devices, barely 1 to 5 false alarms as a reference that's approved today. So we need to use a completely different strategy. Partition into 30 seconds is too smaller of a granularity, but if you only worry about computation tools, you probably don't think about that. My algorithms is very good, deep learning got nothing to improve further, right? But then there's a fundamental gap to application and usability that just cannot be overcome. So that's kind of the scenarios we're examining with this. And my team involves students, colleagues, and we have other funded ongoing projects. And so the second part is, how do we build the team? How did we build the team for this particular application? In general, we're not actually building the team just for the smart habits. You have to have a long-term commitment. So build trust, establish long-term relationship, share values. You have to share some certain values, because otherwise your relationship cannot be long-term. Open and fairness in communication, recognition, and be selective. We already talked about the leading domain expert. You can't just grab somebody else who's the doctor and then, oh, he's domain expert. So that may not work. I mean, all of those attributes is actually like finding, it's like marriage. It's long term. You have to think about that way. And then, you know, there are many things you can do after you have the right team. And applying for Smart Health program, what are the lessons I have learned? Because this is not the first time I actually applied 3 times of different topics. And this is almost like this one particular is almost like a resubmission. And identify and articulate truly important problems. That should be fundamental. And work with real-world data and work with leading domain expert and who can interpret that data appropriately. Proposals overall logical flow needs to be tight. That is actually part of the scientific rigor. Scientific rigor is not just a proof of a theorem that's rigorous, but actually your overall logical thinking, the steps you're taking from A to B to C, does it let you from B to C? You say you from B to C, but maybe there's a large gap that's not clear. Evaluation needs to tie back to the original challenge and problem has to be linked to that and cannot be just then focused, oh, I introduced this technique and then we just evaluate this technique. That's not sufficient to me. And present less formula, more interpretation of what it means in the formula, and also understanding of that in the context. Set expectations properly. I learned a lesson to avoid adjectives as much as possible. This is important because each time you introduce an adjective, you're really raising the expectation of the reviewer. And then too many of the higher expectations will, you know, raise questions. And also put yourself in the shoes of the reviewer. How would the reviewer look at the proposal? Here we have an example of adjectives, you know, large scale, highly efficient, scalable, and things like that. That's actually lifted from the sample proposal. I was looking for that. Those places, there's nothing too substantive for those parts. So in the end, I want to close with platform kind of thinking. Many areas, the internet brought fundamental revolution, like taking Uber, you know, cloud and things like that. But for healthcare, it's like the last grand challenge. It's so hard to transform healthcare itself. And we need to consistently put pressure and work on that and use a platform thinking like business has been revolutionized, leveraging the Internet of Things. And I think the opportunity is still in front of us. So what would be the fundamental platform revolution for healthcare? That's part of the, I hope SCH program can help us get there. Thank you.